Good morning, good afternoon, and good evening to all our customers joining us from across the globe. Hello, everyone. My name is Lokesh Charara, and I'm the Senior Manager for the Arista Technical Services team. And on behalf of the entire team, I extend a warm welcome to each and every one of you who are joining us for this remarkable webinar series graciously hosted by the Arista Technical Services team. For our customers who are joining us for the very first time or maybe joining us after break, I will quickly cover a few details about this initiative. Vignesh, let's move on to the next slide, please. So our aim with these webinar sessions is to work on sharing the knowledge that we cultivate here in our risk attack world with our customers and cover the topics which are most useful and applicable to all of our customers in depth. We started this effort in 2022, and we covered some basic topics like switch health checks, upgrades, and the maintenance planning. In 2023, we hosted 9 sessions where we shifted our focus more onto the technical topics like Layer 2 and Layer 3 debugging, VXLAN debugging, and EVPN debugging from the EOS CLI and Cloud Vision perspective. Recording of all our previous sessions, including the presentation material and Q&As, they are available on our Arista community page if you would like to review it. The links for that are going to be available in the slide deck as well. So coming to 2024, starting this year, we are going to bring in more Arista products in the mix and do a deep dive into how these products together can offer a helpful platform for debugging any common networking problem. For today's session, we are going to do a deep dive into network latency and the congestion issues that can occur in any network. And we are going to cover some use cases that we see in our TAC interaction and common problems that can occur in any network, whether it be a data center or campus network. We'll also go over the debugging steps that can be applied to troubleshoot these network problems and the CLI tools that will come handy in such situations. So for today's session, we have our technical lead, Vignesh Jyotinarayanan, who will be walking us through these debug scenarios. So Vignesh will take us through some lab scenarios that we have encountered in our TAC interaction. And for everyone's reference, we have prepared a lab topology diagram that we already sent out to our registered customers earlier this week. And Vignesh will be highlighting this topology in between as well during the debug scenarios, but it'll be a good idea. And I definitely recommend everyone to take a screenshot of this topology for your reference. We have a PDF link available in the Q&A section that our panelists are putting now. So please download it and keep it handy during the course of this presentation. Along with Vignesh, we also have our technical leads as part of this panel who can help answer any questions that you may have during the presentation. You can use our Q&A manager to ask our panelists any question. But before I, we move on to the next course of this presentation, I would like to highlight our new product offering that is TAC Custom Training. Vignesh, can you move on to the next slide, please? Thanks. So based on the valued feedback that we have been receiving from a lot of you and just a wider interest in the personalized trainings, we actually have kicked this effort off, which is essentially a fully customized training session led by our TAC experts. We customize the content of these sessions based on the feature set, platforms, design that you have in your network environment. And we also include comprehensive analysis of the recent TAC cases as part of these sessions to provide you a 360-degree view of your network and the problems that you've been experiencing in your network, along with the key recommendations that come from our TAC experts to overcome these problems and in order to avoid outages. These sessions actually get delivered as in the form of debugging scenarios to ensure the readiness of your network operations team to handle any such challenges. Since we started this offering, we have delivered many such sessions to our cloud titans and the enterprise customers, and we continue to receive really great feedback on the quality as well as on the content. This is a paid offering, and if you're interested in scoping a session with us or just interested in learning more about this offering, please do reach out to us on tac-custom-training@arista.com. With that, without taking any further time, I'll hand it off to Vignesh for taking you through the presentation. Vignesh, take it away.
Thank you, Lokesh. Hello, everyone. Welcome to TAC Webinar Series 2024. And this is the first session in 2024. And in this session, we will be covering how to effectively troubleshoot network latency issues. I'm the speaker for today's session, and my name is Vignesh Jyoti Narayanan. I'm the technical lead TAC at Arista Networks. So let's go over the highlights of this session before we dive into the actual troubleshooting scenario. Troubleshooting complex issues are always time consuming. In order to solve this problem, Arista also builds tools which are efficient to use, especially in complex scenarios. So for the scenario we're going to deal today, which is one of the complex ones like intermittent network latency issues happening on the network, we're going to use tools from Arista like Arista's Network Observability Solution or DANSI Monitoring Fabric, Arista Switch CLI with rich set of debug commands, and Cloud Vision. Part of TAC Webinar Series 2023, we have covered comprehensive usage of Arista Switch CLI with rich set of debug commands and Cloud Vision for various troubleshooting scenarios. So they both doesn't require a special introduction, but Arista's Network Observability Solution or DANSI Monitoring Fabric is a new addition to the list of tools being used in this session. So let's get to know about that before we dive into the actual scenarios. DANSI Monitoring Fabric, or DMF in short, is a next generation packet broker network solution which has a scalable fabric controlled by DMF controllers. In its scalable fabric, it has DMF filter switches, core switches, and delivery switches. Apart from that, it also has some specialized nodes like analytics node, recorder node, and service node for various use cases. Let's say you wanted to perform a network performance analysis on your production traffic or any form of security threat hunting on your production flows. The easiest way to do that is by mirroring those flows or spanning those flows all the way to the DMF filter switches by sending one copy of it to it. And DMF filter switches can filter the traffic based on the rules we write. Once the traffic is filtered, we can divert the traffic to any of the traffic analyzer tools connected to the delivery switches. In our troubleshooting scenarios today, we also have a production fabric, which is actually sending mirrored copy or spanned copy to the DMF filter switches. And we are filtering those copies in the filter switches and diverting them all the way to the DMF recorder node for recording those packets so that we can take a look at it at a later stage. Please note that you can use any network packet broker solution for this kind of troubleshooting, but in my example, we are using Arista DMF. Okay, since we got to know about the DMF and its use cases, it's time for us to discuss the troubleshooting scenario. Please note that this is a demo of the issue happened on Jan 15 between 2:30 to 2:40 p.m. PST on the network. And troubleshooting for that issue was performed a little later on the same day. Okay, let's dive into the detailed problem description now. So customer was able to see some poor application performance in the network. And these were happening for various hosts part of multiple VLANs, and they were not able to pinpoint or narrow it down to a particular subnet or VLAN. So the issue seems to be happening intermittently. And last time when the issue was happened, it was on Jan 15 between 2:30 to 2:40 p.m. PST. And while we are troubleshooting, the issue seems to be not happening, but we should figure out the issue and root cause it before the next wave hits. So in order to help us with more data points, they also performed a few tests and captured those outputs during the last issue window, that is between 2:30 to 2:40 p.m. PST. The first test they performed is the SCP file transfer test between the server 1 trying to send a file to server 2. And they were able to see a very slow transfer rate. And the test 2 is the ping test between the same servers. And they were able to see a round trip time close to 1 second or 1000 milliseconds for each and every pings. So as of now, we just know where the server 1 is connected to. We don't know where the server 2 is actually connected to in this topology. We got to trace the path between the server 1 all the way to the server 2 while we are performing the troubleshooting. Okay, this seems to be an interesting problem where the issue seems to be happening intermittently, and it's a network latency issue. And we don't know when this might resurface again, but we are presented with a challenge to troubleshoot this and figure out the problem and provide the fix before the next wave it's causing network-wide latency issues. Okay, let's troubleshoot with the data we have in hand for now. Before we dive into the actual troubleshooting, let's take a deeper look at the outputs captured by the customer during the last issue window, that is between 2:30 to 2:40 p.m. PST on Jan 15. On the screen, you see the first snippet, that is the SCP file transfer test performed from the server 1 trying to send a file to the server 2, that is 192.168.100.252. And we were able to see a very slow transfer rate. Based on the ETA for the file transfer to complete, we see around 2 hours 34 minutes. But customer expecting the file transfer should have been completed within a minute during non-issue time. The next snippet which you see on the screen is the ping test from the server 1 trying to ping the server 2's IP, that is 192.168.100.252. And we were able to see a round trip time close to 1000 millisecond or 1 second latency. So when comparing this data with a non-issue time for the similar ping, we were able to observe only 0.2 millisecond as round trip time. So we see a huge latency during the issue time versus non-issue time, like the huge latency difference. So these kind of huge latency difference are usually caused by issues like congestion happening in one or more nodes in the path which is forwarding these packets, or it can be some sort of software forwarding instead of an hardware forwarding happening on one of those devices. So there can be many other reasons as well for these kind of high latencies, but most commonly we will see this issue when there is some congestion or software forwarding happening. Okay, with the data we have in hand, let's troubleshoot this issue. Okay, we know that the ping between server 1 towards server 2 was impacted during the time of the issue. That is, server 1 is owning the IP address that is 192.168.100.251, and it's owning the MAC address ending with 8A59. And server 2's IP address is 192.168.100.252, and it's owning the MAC address ending with C361. During the time of the issue, they were able to see a latency close to 1000 milliseconds. So since they saw the issue on this flow, we're going to use this flow for our troubleshooting. Okay, before we dive into the troubleshooting, let's trace the path between server 1 and server 2 to figure out a couple of more data points for us. Tracing the path between the servers and the flow is important for a couple of reasons. The first main reason is tracing helps us set the scope for the problem. So we know that there can be many devices in the path forwarding these packets end to end, but while tracing the path, we get to know the exact devices which will be involved in this forwarding. So we can focus more on those devices. This is especially useful in deployments where we have more than hundreds of devices in the fabric. The second reason tracing is important is we'll get to know the control plane states like MAC address table learnings, routing table entries, etc., so that we can compare them during non-issue time versus issue time so that we can pinpoint potential issues. Okay, so let's get started with the tracing of the path between the server 1 all the way to the server 2. Okay, first, I'm going to initiate a ping from the server 1 towards the server 2. So I'm directly entering the ping command in the CLA session, and I'm limiting the ping to just 4 pings for now. And as of now, I can see the round trip time is just 0.2 millisecond. So as we discussed earlier, the issue seems to be happening intermittently in customer fabric, and they were able to see the issue between 2:30 to 2:40 p.m. PST on Jan 15. But we are troubleshooting little later on the same day where we were not able to see the problem, but we need to figure out the problem before the next wave hits. Okay, so As of now, what we know is the server 1 is connected to the leaf 1 and leaf 2 MLAC pair over the port channel 10. And if you take a closer look at the server 1's IP and the server 2's IP, they're both part of the same subnet. So most likely they are part of the same VLAN as well. So in that case, so let's go ahead and check on the leaf 1 and leaf 2 for its MAC address table entry to see where the server 2's MAC is learned. So for that, I'm logging into the leaf 1 and leaf 2, and I'm going to check the MAC address table entry. For that, I will be using show MAC address table command on leaf 1 and leaf 2. Okay. While checking the show MAC address table output on leaf 1, we can see that the server 1's MAC is learned over port channel 10, which is the MLAC port channel that is expected. Okay, let's check out on the leaf 2 as well. On the leaf 2 as well, we pretty much see this same thing, that is the server 1's MAC that is ending with 8A59 is learned over port channel 10. Okay, now it's time for us to check the server 2's MAC. Server 2's MAC ends with C361. Let's check it out. So the server 2's MAC is actually learned over VX1 interface. So VX1 interface means it's a VXLAN interface. So since we see that the server 2's MAC is actually learned over VX1 interface, now it's time for us to actually discuss more on this topology to get a better understanding. So as we know, server 1 is connected to leaf 1 and leaf 2, and leaf 1 and leaf 2 are an MLAC pair, and they are also an Anycast VTUP owning the VTUP address 10.11.11.11. Likewise, leaf 3 and leaf 4 are another MLAC pair owning the Anycast VTUP address that is 10.22.22.22. And then we have leaf 5, which is a standalone VTUP owning the VTUP IP that is 10.33.33.33. And there is another leaf, which is leaf 6. It is a non-VTUP, and we see that it is directly connected to leaf 5. Between the leaf VTUPs, the connectivity is provided with the help of spine 1 and spine 2. And the fabric we are dealing with is a VXLAN EVPN fabric. And in order to share the MAC address learning between the VTUPs, we are using BGP EVPN control plane. Okay, since we got an idea about the topology we are dealing with, and leaf 1 is telling that the server 2's MAC is learned over VX1 interface. So now it's time for us to understand where the server 2 is connected to and which VTUP it is actually connected to. For that, let's use the show VXLAN address table command on leaf 1 and leaf 2. Okay, I'm using the show VXLAN address command on both leaf 1 and leaf 2. And I get to see that the server 2's MAC ending with C361 is actually learned from the VTUP IP that is 10.22.22.22, and we can see it is learned via the EVPN control plane. Okay, since we know that the server 2 is actually learned through the VTUP that is 10.22.22.22, in order for the server 1's packet to reach the server 2, it can either go to leaf 1 or leaf 2 now. And from leaf 1 or leaf 2, since it's a bridging flow and the same VLAN flow, leaf 1 or leaf 2 now need to encapsulate those packets in a VXLAN encapsulation and send it over to the remote VTUP IP that is 10.22.22.22. In order to send it over to the remote VTUP IP, we need to know the route to reach the remote VTUP IP. So let's check that out on leaf 1 and leaf 2. For that, I'm going to use show IP route 10.22.22.22 command to check the route to reach the remote VTUP address. Okay, let's use the command here. Show IP route 10.22.22.22 on both leaf 1 and leaf 2. Okay, we get to see that on leaf 1 and also on leaf 2, there is an ECMP path to actually reach the remote VTUP address that is 10.22.22.22. So an ECMP paths are via the ports ET49/1 and 50/1 on both of them. So let's also check the LLDP neighbor output on these ports to get to know the link partners part of these ports. To show LLDP neighbor ET49/1 and 50/1 on both leaf 1 and leaf 2. Okay, so we get to see that once the VXLAN encapsulation is performed by the leaf 1 and leaf 2, it can either send the packet over to spine 1 or spine 2 in order to reach the remote VTUP address that is 10.22.22.22. Okay, So now it's time for us to go and check on the spine devices to trace the path until the server 2. So let's log in into the spine 1 and spine 2 now. I'm going to check starting with the route table entry to reach the remote meetup address. The reason is, since the packet once reached to spine 1 or spine 2, it will be a VXLAN encapsulated packet. The spine will route the packet based on the remote meetup address. So we can check the route table entry to reach the remote meetup address here on spine 1 and spine 2. Okay, so on spine 1, we get to see there is an ECMP route pointing via the paths ET1/1 and 3/1. The same appears to be true on the spine 2 as well. So now let's also check the LLDP neighbors for the interfaces. For that, I'm using show LLDP neighbor command for ET1/1 and 3/1. Okay, so we get to see on the spine, based on the ECMP path, it can either forward the packet over to leaf 3 or leaf 4. The same appears to be true for even the spine 2. So it can either forward the packet to leaf 3 or leaf 4. So now it's time for us to check on the leaf 3 and leaf 4 to complete the path trace end to end. Okay, so on the leaf 3 and leaf 4, we can also check whether it is actually playing the VTEP role or not. So using the command show interface VXLAN 1, and while checking on that, we can see that leaf 3 and leaf 4 are playing the VXLAN VTEP role, and they are owning the Anycast VTEP address that is 10.22.22.22. Okay, since leaf 3 or leaf 4 are playing the VXLAN VTEP role, and the packet it received from spine 1 and spine 2, it's a VXLAN encapsulated packet destined to 10.22.22.22 address. So it's the leaf 3's or leaf 4's responsibility to actually decapsulate this packet and forward the packet to the destination as per the MAC address entry, because it's an L2 VXLAN flow. Okay, so for that, we can take a look at the MAC address table entry on leaf 3 and leaf 4. So let's use show MAC address table command on both leaf 3 and leaf 4. And we know that the server 2's MAC is ending with C361. So let's check it out where it is learned on. We can see that the server 2's MAC is learned via the port channel 10, and the server 1's MAC is learned via the VX1 interface. Server 1's MAC is ending with 8A59. So that kind of completes the path trace between the server 1 and server 2. So if you notice in the topology diagram shown on the screen, between the server 1 and server 2, we have 6 Arista switches in the path. So in order to figure out which switch or which node actually kind of added this extra latency while sending the ping packets between the server 1 and server 2 during the time of the issue, one way is to log in into each and every device and check for any evidences of congestion which could be happening during that time between 2:30 to 2:40 p.m. PST. But if you notice this topology, the number of devices in the path is just 6. It's very less when compared to the things you usually might see in the field. So on the screen, you see 2 topologies. The one on the left is the TAC webinar topology, which we are using, the trace path between server 1 and server 2. And the one you see on the right is an example topology, which you might see on the field, where server 1, server 2 is connected to the leaf VTEPs. And these leaf VTEPs are actually connected with the help of a 16-way ECMP spine. So there can be more number of ECMP spine as well in the path. So this kind of adds up more number of devices in the path for us to individually take a look at each and every devices. Likewise, there are few other scenarios as well. So let's explore that as well. So on the screen, you see 2 other examples where the similar leaf VTEPs can be connected in a way that there is a multi-layer spine. There is a regular layer spine and the super spine layer on the topology you see on the left. So this also adds more number of devices in the path. Likewise, on the right side of the screen, you see another topology where these leaf VTEPs can be present in a way that they are separated part of 2 different sites, and both the sites are actually connected with the help of spine layer in their site and also border leaves through the DCA link. So if you notice here, there seems to be many number of devices possible in the path between the server 1 and server 2. So Since we have a lot of these devices in the path, given the number of devices in the path, how to troubleshoot this issue efficiently? It is very time consuming and it also a hard task to go and check on each and every devices for any evidences of condition. And to add with more complexity, the issue is also not happening right now. It happened in the past and we got to root cause it. So how to efficiently troubleshoot this issue in this scenario? Okay, so there has to be some efficient way, right? At the start of this session, we briefly touched upon the use cases of DANC monitoring fabric and network packet broker solution. So we are going to leverage that here in this troubleshooting. So let's take a look at how it's going to help us and the idea we're going to use here. Okay, we know that the server one, when it sent a ping towards server two during the time of the issue, customer was clearly able to see a latency close to 1000 millisecond. So we're going to take a look at that exact ping packet that was sent during the issue time, which was traversing through these devices in the path all the way until the server 2 to tell which device was adding this extra latency to those packets. So in order to figure this out, so we need to take a look at those historic packet captures, right? The packet captures which were done during the time that is 2:30 to 2:40 p.m. PST. In order to help us, so we have this DMF packet broker fabric to provide those packet captures for us. So all these devices are already mirroring those production flows or spanning those production flows and sending one copy of them to the DMF filter switches. And DMF filter switches were filtering those important flows, and those were actually recorded on the DMF packet recorder node. And this DMF packet recorder node will provide us that packet captures for us to go back and check what happened to those packets during the time of the issue. Before saving the packets into the DMF packet recorder node, we are also performing the VXLAN header strip action to those packets, where we are stripping the VXLAN headers since it's a VXLAN fabric. And let's say the VXLAN header is stripped and the packets are saved in the DMF recorder node. In order to tell which switch actually the copy of the packet came from, we're also adding extra span VLAN device ID on the DMF filter interfaces while we are getting the traffic. For example, on the spine one, when it's sending its mirroring copies towards the DMF filter switches, we are also adding it with one extra span VLAN tag, that is 2106. So all the copies, all the mirrored copies from spine one will have 2106 while we are taking a look at the packet captures. So likewise from spine two, we are adding with 2109. For leaf one, we are adding with 2103. For leaf 2, we are adding with 2108. For leaf 3, we are adding 2101. And leaf 4, we are adding 2107. Okay, since we got an idea about how we are going to efficiently troubleshoot this scenario, okay, let's go ahead and take a look at the DMF controller to get the packets for analysis. Okay, let's log into the DMF controller now. Okay, on the screen, you see the DMF controller dashboard. From this dashboard, we are going to navigate to DMF recorder node dashboard. And from there, we can perform a query to actually get the packet capture file out, and we can analyze it through the Wireshark. Okay, let's go to the DMF recorder node dashboard now from here. For that, let's click the monitoring tab in the top. And then from the drop-down menu, let's click recorder nodes. Okay. On the screen, you will see the DMF recorder node dashboard. Okay, so on this recorder node dashboard, let's scroll through and navigate to the section where we can actually perform the query. Okay, this is the section to perform the DMF recorder node queries. So there are few important parameters we need to focus on before we can actually perform the query. So the first is the query type. I'm setting it to packet data. The reason is the reason is we are going to get the packets as a packet capture file so that we can take a look at it using the Wireshark. So that is the reason I'm setting the query type to packet data. Next thing is we need to set the timestamp or the time range for us for the DMF recorder node to fetch the packets out for us. So we know that the issue was happening on Jan 15 between 2:30 to 2:40 p.m. PST. So I need to set a time range which actually covers that time range. So I'm setting the from time here to 2:30 p.m. PST on Jan 15. So likewise on the to range, I can set it to any time which actually comprises that issue time window. So issue time was between 2:30 to 2:40. So let's set it to 2:30 p.m. to 3 p.m. here. So let me go ahead and set it here to 3 p.m. Okay, now we have set the parameter for the recorder node to fetch all the packets around this time range. Okay, now it's time for us to filter the packets, right, with an IP address. Otherwise, we would get a lot of other packets as well in our packet capture. So I'm setting the server one's IP address here. The reason is we are focusing on one ping echo request from server one traversing through all the switches during the time of the issue towards server two, and one ping echo reply from server 2 reaching towards server 1 traversing through these devices to pinpoint which node was adding this extra latency. So I'm setting the IP address of the server 1 here so that I can fetch both packets from server 1 and also received by the server 1. Okay, that's the reason I set it to 191.168.100.251. The next thing I wanted to set is the ICMP filter here on the IP protocols. The reason is since we are focusing on only the ICMP packets for now, so I'm setting it to ICMP so that we will get less number of packets in the PCAP file, okay, to focus on. Okay, since we have put together all the important parameters here to submit the query, now it's time for us to submit it. Okay, let's click the submit query button here. And once we submit it, we'll get to see a link provided by the DMF recorder node. And once we click the link, we can download the PCAP file. So as you can see, there is a file URL link provided by the recorder node. So let's go ahead and click that link to download the PCAP file. Okay, so once we click the link, we can download the PCAP file to our local machine. And now it's time for us to take a look at those PCAP file in the Wireshark. Okay, let's check it out, Brad. So now I'm going to open that PCAP file in the Wireshark. Okay, so in order to save time, what I did is I already set up the filters in a way that filters on the Wireshark in a way that it actually shows only one ping echo request and one ping echo reply, which was traversing through the switches during the time of the issue, that is between 2:30 to 2:40 p.m. PST. And with this packets, we can actually figure out which node or which set of node was actually adding this extra latency. Okay, so you will see there are 6 echo request packets and 6 echo reply packets showing up on the screen. Why it is 6? The reason is we have 3 set of nodes in the path. So the packets from server 1, in order to go to server 2, it can either traverse through leaf 1, leaf 2, or spine 1 or spine 2, or leaf 3 or leaf 4. Since we set up mirroring in a way from each and every device that it actually mirrors both ingress copy of the packet eating the device and also egress copy which is sent out of the device. So on each and every set of node it's traversing, we will see 2 copies of the packet, which is ingress copy and egress copy. So we have 3 set of nodes and 2 copies from each devices. So 3 into 2, it has a 6 packets in the echo request and 6 packets in the echo reply. Okay, now it's time for us to take a deeper look at this packet captures to figure out which node was adding this extra latency. For that, we need to focus on 2 key information. One is the timestamp on those packets, and the second one is the span VLAN device ID, which was added by the DMF to each and every packet. Okay, the span VLAN device ID tells which leaf node the packet came, a leaf node or spine node the packet came from, and the timestamp tells us whether it is adding the latency or not while the forwarding happens. Okay, let's take a look at them now. So on the forward direction, we see the server 1 was actually sending the packet to leaf 1, and from leaf 1 it is sent towards the spine 1, and from spine 1 it is actually sent towards the leaf 4. But one interesting thing we can note while it is being forwarded out of spine 1, if you compare the ingress timestamp and egress timestamp of the packets reaching the spine 1 on the forward direction, we see there is a clear 1 second or 1000 millisecond latency added to that packet. So which kind of aligns with the observation made by the customer during the issue time, where they were able to see 1000 millisecond latency added to those ping flow, right? So that seems to be shown up here, where it is getting added to the packet sent out of spine. Okay. Now, after that, the spine actually sending the packet to leaf 4, and from leaf 4, it is finally reaching the server 2. So in the forward direction, the packet from server 1 going to leaf 1, and from leaf 1, it is going to spine 1, and from spine 1, it is going to leaf 4, and from leaf 4, it is reaching the server 2. So this is also highlighted in the topology diagram I put together on the screen, where we have the red arrow showing this packet flow in an exact path. So while it was traversing the spine, it was added with an extra latency close to 1000 millisecond. Okay, so now let's figure out what is the reverse path of it. In the reverse direction, the echo reply packet from server 2 was actually landing on the leaf 4, and from leaf 4, it is actually going to spine 1, and from spine 1, it is going to leaf 2, and from leaf 2, it's actually reaching the server 1. So this exact path was put together in a topology diagram as the blue arrow, which you see going from the server 2, it goes to leaf 4, and from leaf 4, it goes to spine 1, and from spine 1, it goes to leaf 2, and from leaf 2, it goes to server 1. So one interesting thing to note here is, while checking the timestamp, we were not able to see any extra latency kind of added apart from the regular forwarding latencies on this reverse path. So it looks like we were able to figure out few information with this data. That is, first thing is the exact path of the packet during the time of the issue, given there are ECMP paths in the fabric. And second, we were able to identify that spine 1 was the device which was adding this extra latency to the packets during the time of the issue. And that too, it is only adding adding this latency only in the forward direction. It was not observed on the reverse direction. Okay, since we figured out that spine 1 was adding this extra latency, now the question rises that why spine 1 was adding this latency only during the time of the issue. And customer observed that this issue was intermittent. And when we also tested with the ping test between server 1 and server 2, we were not able to observe the latency at present, because at present, currently the issue is not happening. It happened earlier. So why it happened only during the issue time? So ping kind of pretty much ashes in the same way that it goes through the same exact path in the VXLAN fabric. So if the issue was always present, we should have also seen the issue while we were trying to ping as well. But spine 1 was for some reason adding the latency only during that issue window, that is 2:30 to 2:40 p.m. PST. Okay, so in order to figure out why spine 1 was adding this extra latency during that time, so we need to go back in time and check on any events for spine 1 which we can correlate to this extra latency, right, added to the packets. So for that, we're going to leverage cloud vision. So all the switches are already configured in a way that they kind of stream telemetry to the cloud vision, and cloud vision actually checks the counters and various things, part of the telemetry, part of each and every devices, and flag them up as events if it finds anything out of range. So let's go ahead and check on the cloud vision to check whether there were any events happening on spine 1 during the time of the issue. Okay, let's log in into the cloud vision now. Okay, on the screen, you see the cloud vision dashboard. Here we see all the devices which are streaming to the cloud vision. And from here, let's navigate to events dashboard. So I'm going to click the events dashboard. Okay, in the events dashboard, we'll get to see all the events from all the devices. But in order to focus on the spine related events, I put together the filter in a way that it shows only the spine 1 and spine 2 events. Okay. So now we have filtered it only to the spine 1 and spine 2 events. Let's focus on the events happening on spine 1 and spine 2 during the time of our problem, so that we can figure out the possible potential reasons why spine 1 was adding this latency. So while checking on these events, we were able to see there seems to be some congestion related events happening in a wave in an intermittent fashion. which kind of aligns with the customer observation as well. Customer was able to see there was some intermittent latency problem, right? So we were able to see the same pattern here as well. And the events happening on spine 1 or spine 2 seems to be mostly congestion related events or packet drops related to congestion. Okay, let's take a look at the events which were exactly happening to our which aligns with our last issue window, that is 2:30 to 2:40 p.m. PST. So while checking it out, we were able to see 4 events happening during that time. The events related to congestion was happening on interface ET3/1 on spine 2, ET1/1 on spine 2, ET1/1 on spine 1, and ET3/1 on spine 1. So if you focus on the topology, these interfaces on spine 1 and spine 2 are the interfaces which were actually facing towards the leaf 3 and leaf 4. So spine 1, ET1/1, 3/1 are the interfaces connected to leaf 3 and leaf 4. And spine 2 interfaces ET1/1 and 3/1 are the interfaces facing towards leaf 3 and leaf 4. So there seems to be some congestion event happening on these interfaces during the time of the issue, so that these congestion events are actually causing trouble to the other flows which were traversing through the same flow. One such flow is even the ping test customer performed, so which was getting added with high latency. Okay, now let's take a look at these events in detail. So now let's click on the first event which we see during the time of the issue. That is the event happening on ET3/1 on spine 2. Let's click that. One thing before that is we noticed that the congestion related events happening on both spine 1 and spine 2. So even though we identified that the spine 1 was the one which was adding the latency during that time, but it looks like this congestion event is widespread across both the spines as well. So that's the reason we are checking all the 4 events on the spines during that time. Okay, let's check the first event now. The first event you see on the screen is the congestion event happening on ET3/1 on spine 2. Cloud Vision, apart from highlighting the events, it also provides some correlated event analysis where we can get more insights from. So as you can see, during that time on the ET3/1 interface on the spine 2, we were able to see there seems to be an increase in the traffic rate on that interface. And around the same time, we were also able to see some congestion related discards happening. And Cloud Vision also highlights the fact that this is the interface pointing towards leaf 4 based on the LLDP neighbor output. And then while also comparing it with the latency analyzer data, we see that there seems to be an increase in the buffer usage on that port. And there seems to be congestion related drops happening in Q1 related to that interface. And it also highlights the fact that there seems to be no ARP table or routing table changes happening on the spine 2 during the time of the issue. Okay, let's check it out, another event which happens around the same time. Okay, let's click on the second event happened during the same time. Okay, this event happened on ET1/1 on spine 2. Okay, we can see that there seems to be an increase in the traffic rate again here, pretty much aligns with the similar pattern we saw on another interface on spine 2 facing towards leaf 4. And pretty much we were able to see increase in the traffic rate and congestion related discards. And this is the interface facing towards leaf 3 from the spine 2. And similar observation on the buffer usage. During that time, buffer usage was increased and there were some congestion related discards happening as well. And around the same time, we get to see that the ARP table and routing table seems to be stable. As you can see, there is a flat graph like we saw for the earlier event as well. Okay, let's check it out, the other 2 events as well, which were happening during the same time. Okay, let's click on this event happening on ET1/1 interface on spine 1. Okay, pretty much similar observation is being observed here. The traffic rate seems to have increased during that time, followed by congestion related discards. And Cloud Vision highlights the fact that this interface, the interface facing towards leaf 3, and there seems to be increase in the buffer usage and followed by congestion related discards happening. And there seems to be no changes to the ARP table or routing table entries during that time. Okay, that's interesting. Okay, let's check the final event, which was related to congestion during that time happening on spine 1 interface. Okay, this event happens on ET3/1 on spine 1, and pretty much similar observation where we can see increase in the traffic rate during the same time, that is 2:30 to 2:40 p.m. PST, followed by congestion related discards. You can see the discards out, and then the LADP neighbor output tells that it is the interface facing towards leaf 4, and increase in the buffer usage is observed based on the latency analyzer output, and followed by congestion related discards happening. And there seems to be no changes to the ARP table or routing table during the time of the issue. Okay, so kind of correlating all these 4 events happening on spine interfaces facing towards leaf 3 and leaf 4, we get to see a pattern where there seems to be an increase in the traffic rate during the time of the issue on these 4 interfaces from spine 1 and spine 2 facing towards leaf 3 and leaf 4. And this increase in the traffic rate was actually causing the congestion on that port. And that congestion was finally causing trouble to other flows which are also passing through the same interface, like forwarded through the same interface. And finally, we were able to observe high latency issues. Okay, we understood that there seems to be an increase in the traffic rate, isn't it? So we need to know what were those flows which were actually causing this increase in the traffic rate, and in turn congesting that port on spine interfaces facing the leaf 3 and leaf 4. Okay, so we need to know what were the flows responsible for this congestion. So the puzzle isn't really solved until we figure it out, what were those flows, right? So for that, we can take a look at the S-flow related data, which are top talkers, so that we can figure out what were those flows which were causing this increase in the traffic rate during the time of the issue. So we can check the S-flow related data on the spine devices during that time. Okay, so Cloud Vision also going to help us for checking this S-flow related data, because all the switches are already configured in a way that they are also streaming the S-flow flow records to the Cloud Vision. So we're going to use the Cloud Vision to check those things as well now. Okay, let's go back to Cloud Vision to check the S-flow flow records during the time of the issue. Okay, so we are back to the devices dashboard, and we're going to navigate to Spine 1's device overview to check for the S-flow records. So on the Spine 1, I'm going to navigate to the traffic flows dashboard, which you see on the side. Okay, so on the screen, you see the traffic flow dashboard of the Spine 1. And if you closely look at the graph shown here, during the time of the issue, that is between 2:30 to 2:40 p.m. PST, we see there is an uptick in the traffic from some of the sources like 10.100.200 network. Okay, that seems to be aligning with the customer observation. But let's also check the detailed flow records and top talkers data during that time. Okay, while checking on the flow records, we were able to see a pattern where the flows were actually originating at the timestamp that is 2:30 p.m. PST. So the start time of this flow were around 2:30 p.m. PST on Jan 15, and then it has ended around 2:40 p.m. PST. So that kind of pretty much aligns with the issue window provided by the customer, at 2:30 to 2:40 p.m. PST on Jan 15. Okay, so let's also analyze what were the sources of this traffic. So sources of this traffic pretty much are from 10.100.200 network. And if you check the topology diagram put together on the top, this source network is pretty much attached to the leaf 5, as you can see on the topology. Likewise, let's also check it out the destination of this flow. The destination IP address for this flow pretty much are part of the subnet 10.100.100 network. And if you again focus on the topology diagram, we see that this destination network is attached to leaf 6. Okay, so it looks like source is attached to leaf 5 and destination is attached to leaf 6. But when we check the S-flow flow records on the spine 1, we get to see these flows eating the spine 1. That seems to be weird, right? So let's check it out on the ingress interface on which the spine 1 actually received these flows. So on the spine 1, the ingress interface is ET13/1. That is the interface which is connected to the leaf 5. So it looks like these flows were from the leaf 5. So leaf 5 for some reason was forwarding these flows to the spine 1 instead of directly forwarding it to leaf 6. Okay, that seems to be happening. Fine. Okay, let's check it out. Which interface the spine was actually sending these flows out during the time of the issue. Okay, let's check it out. The egress interfaces. Okay, the egress interfaces seems to be either ET1/1 or 3/1, as you can see on the screen. So if you again focus on the topology diagram, these interfaces on the spine, that is ET3/1 and ET1/1, are the interfaces which are connected towards the leaf 3 or leaf 4. So it looks like these flows are entering to the spine device from the leaf 5, and from spine 1 it is getting forwarded to either leaf 3 or leaf 4. Okay, let's check what's the status on spine 2 during the same time. Let's also check the spine 2's flow records. So let's click the spine 2 flow records now. Okay, while checking on the spine 2 flow record, let's check the start time of this flow. The start time seems to be 2:30 p.m. PST, just like what we saw in the spine 1, and the end time seems to be 2:40 p.m. PST. Okay, and then we see the sources are from pretty much the same sources, that is 10.100 or 200 network, and those devices are looking to be connected to the leaf 5. And let's check it out. The destination of this flow, the destination seems to be 10.100.100 network, and that is connected to leaf 6. So it's pretty similar pattern what we observed on spine 1. So the ingress interface for these flows seems to be ET13/1. If you take a look at the topology diagram on the spine 2, ET13/1 is the interface facing towards leaf 5. So that means leaf 5 was the one who was forwarding these flows to spine 2. And then finally, we were able to see that the egress interface for these flows to be sent out of spine 2 is either ET1/1 or 3/1. So that means spine 2 is actually forwarding these flows out of ET1/1 and 3/1, that is to either leaf 3 or leaf 4. Okay, this seems to be interesting because this is not at all the expected path for this flow. The expected path for this flow is from leaf 5, it needs to directly go to leaf 6, and from leaf 6, it needs to reach the destination. But for some reason, these flows are being received on spine and in turn forwarded all the way to the leaf 3 and leaf 4. Okay, Cloud Vision also provides us a way to visualize these flows in the topology view as well. Let's also take a look at that in the view in topology mode. So I'm going to click one top talker during the time of the issue. Okay, I'm clicking the first one. Okay, so as we discussed earlier, the flow seems to be originated somewhere below the leaf 5 from the test server 1 or test server 2. And from here, it actually goes to spine 1 or spine 2. And from there, it goes to leaf 3. Let's also check another top talker during the same time. Let's go back to the top talker flows and let's click another flow. Okay, so on another flow, we see similar pattern where the packets reach all the way until the spine 1 or spine 2, and from spine 1 or spine 2, it goes to leaf 4. So it looks like these flows are somewhat high bandwidth flows, and these flows for some reason getting incorrectly forwarded towards the spine 1 and spine 2, and from spine 1 and spine 2, it actually sent towards the leaf 3 or leaf 4, due to which we were able to see a problem where it is causing congestion on the spine interfaces facing towards leaf 3 and leaf 4, and this congestion is adding high latency to other legit flows which were forwarding through this forwarded through the same interface. As you can see on the screen, I put together a diagram as well to clearly highlight this, where the blue arrow is the correct path for this test probes from the test servers, and the red arrow is the incorrect path, which we identified that it is flowing through with the help of CVP's traffic flow data. Okay, now it's time for us to log in into the leaf 5 directly to check why leaf 5 was incorrectly forwarding this. Okay, let's check it out on the leaf 5 directly through the CLI session. On the leaf 5, I'm going to start with checking show IP route to reach the destination network for the test probe, that is 10.100.100 at 0. And we get to see there seems to be an ECMP route via the ports ET49/1 and 50/1. Now let's check where these ports are leading to through the LADP neighbor output for ET49/1 and 50/1 on leaf 5. Okay, while checking on that, we see that the ECMP paths were actually facing towards either spine 1 or spine 2. Okay, so does that mean that spine 1 or spine 2 are actually advertising a BGP route to leaf 5 to draw this traffic? Okay, let's check it out on the BGP table output as well. For that, I'm going to use the command show IP BGP, and I'm going to filter it with grep command for the prefix starting with 10.100. Okay, let's execute this. And we get to see there seems to be 3 subnets which are interesting. So there seems to be the /24 subnet 10.100.100.0/24, and there were 2 prefixes received, and both are from spine 1 and spine 2. Okay, so that forms the ECMP route which we see over there. And there is also another route which is the /16 route, which is also received from a next stop address that is 10.9.3.2. Okay, let's check it out. Who is advertising the /16 subnet? So let's use the art table entry to figure out where this next stop address is learned from. It is learned from ET55/1. And while checking the LADP neighbor output for ET55/1, we get to see that, yeah, that's most likely the route received from leaf 6. So which means as per the design path, the traffic from the servers that is 10.100.200 towards the 10.100.100, while hitting the leaf 5, it needs to follow this /16 route and should go towards leaf 6 to get to the final destination for this flow. But since /24 route is also present on the routing table of leaf 5, due to the longest prefix match, we are using the /24 route, and we are incorrectly forwarding the packet towards spine 1 and spine 2. So it looks like the problematic /24 routes are the issue here for this incorrect path flow for these flows. Okay, before going ahead and checking on spine 1 and spine 2 on why it is advertising those problematic /24 routes, before that, let's check on leaf 6 to see whether the /16 route, which we see, is indeed self-originated by leaf 6. For that, I'm using same show IP BGP command with a similar grep filter for all the prefixes starting with 10.100. And we get to see that 10.100.0.0/16 is indeed a self-originated route on leaf 6. So that looks to be a designed the route which the leaf 5 needs to follow. Okay. And we tell that it's a self-originated route is because the next stops field is set to hyphen. So that means the self-originated route from leaf 6. Okay, so now it's time for us to figure out on spine 1 and spine 2 to understand why it is actually sending the problematic /24 route. Okay, for that, let's start by checking the show IP route to reach the destination subnet, that is 10.100.100.0 on spine 1 and spine 2. Okay, on spine 1, we get to see an ECMP path for this subnet. Let's check it out on spine 2 as well for a similar route. Okay, it looks like spine 1 and spine 2 are also having an ECMP path pointing towards the ports ET1/1 and 3/1. So it looks like spine 1 and spine 2 are not the ones who are actually originating this problematic routes. So it should be coming from somewhere in the top. So let's check it out. Who might be those based on the LDP neighbor output? So it looks like it might be from the leaf 3 and leaf 4. So let's check it out, the BGP table output to confirm this. Let's check the show IP BGP output using the similar grep filter, which we used on the other devices as well. Okay, so while checking on this, we get to see that there seems to be the 2/24 routes, which are actually received on spine 1 and spine 2. And those are from leaf 3 and leaf 4. Okay, so it looks like for some reason, leaf 3 and leaf 4 are originating these problematic routes. Now it's time for us to go ahead and check directly on leaf 3 and leaf 4. Okay, let's go to leaf 3 and leaf 4 now to check it out. Okay, on leaf 3 and leaf 4, let's go ahead and start directly with a show IP BGP table output. So I'm executing show IP BGP table output with similar grep filters which we have used earlier. That is for all the prefixes starting with 10.100. Okay, on leaf 3 and leaf 4, we get to see an interesting thing that the /24 route seems to be a self-originated route on leaf 3 and also on leaf 4, which is not at all expected because this subnet is actually connected to the leaf 6. So so that leaf 3 and leaf 4 should not have actually originated this route and advertised to the spine devices. But while taking a look at the deeper look at the BGP table, we also able to identify one /32 route, part of the same subnet, is also self-originated from both of them, both the leaf 3 and leaf 4. Okay, so it looks like some sort of misconfiguration which is present on leaf 3 and leaf 4, which could be responsible for this thing. So let's check it out whether leaf 3 and leaf 4 was having any IP address configured part of the same subnet. So for that, I'm going to use show IP interface brief command, filtered using the grep using the similar prefix, that is 10.100. Okay, so we get to see that on leaf 4, there is a address configured on the loopback interface, which is part of same subnet. And let's also check it on leaf 3 as well. On the leaf 3 as well, we see similar observation. So both on leaf 3 and leaf 4, we get to see there seems to be an IP address configured on the loopback 3 interface from the same subnet. So this is not expected. It looks like for some reason, these subnet was actually used earlier and they migrated the subnet to somewhere on the leaf 6. But after the migration, the IPs which were present on leaf 3 and leaf 4 were not cleared, it seems. So it seems to be causing this trouble. Okay. Now let's check why these routes and prefix are actually advertised into BGP. Because presence of the IP address itself won't advertise into BGP. There has to be some BGP misconfiguration as well along with it to actually advertise these routes into BGP. Okay, let's check it out on the BGP configurations on both leaf 3 and leaf 4 now. So show run section BGP, and we will check it out on for the similar prefix. Any configuration related to similar prefix, that is 10.100. Okay, so this seems to be interesting. We see there is two configuration commands which are related to this issue. One is network command, which is actually advertising the loopback 3 and loopback 4 addresses. And the second thing is the aggregate address command. Okay, so this network command actually advertises a loopback address into the BGP table. So that is fine. That is /32 route. And then this aggregate address command, what it does is it actually summarizes the subnet into a /24 route, 10.100.100.0/24, when there is a presence of contributor route for that subnet. So it looks like the contributor route is present because of the other advertisements. And then due to this aggregate address command, it is also self-originating the /24 route, and it's actually causing the trouble and advertising those things to the spine 1 and spine 2 to draw the traffic all the way until here. Okay, so since we identified there is a misconfiguration here, now it's time for us to remove this misconfiguration here on leaf 3 and leaf 4 by removing the aggregate address command. So let's go ahead and do that. For that, let's get into configuration mode and router BGP configuration on both leaf 3 and leaf 4, and let's remove that aggregate address command to start with. So the expectation after removing this aggregate address command is the leaf 3 and leaf 4, after removing this command, it should withdraw the problematic /24 route from its BGP table. And now that will make changes on the leaf 5 so that leaf 5 will now point to the right route, that is the route via the leaf 6, in order to forward these test probes. Okay, let's go ahead and check on leaf 5 directly to see whether this removal of configuration helped or not. Okay, let's go and check on the leaf 5 for the similar route table entry, which we checked at the start. Show IP route 10.100.100.0. Okay, we get to see that there is a /16 route and it's pointing towards 8055/1 and 8555/1. We can check in the LDP neighbor output. And okay, it looks to be pointing towards the leaf 6 now. So okay, so the config changes which we made on leaf 3 and leaf 4, removing those aggregate address, problematic aggregate address command, helped. As you can see, the leaf 5 is now pointing to the right route. Okay, since we fixed this incorrect path forwarding for this high bandwidth test probes, now it's time for us to check and validate whether this solved the congestion problem in the network, because this incorrect flows were the ones which were actually forwarded towards the spine 1 and spine 2, and these spine 1 spine 2 interfaces facing towards leaf 3 and leaf 4 were congested because of that. And the reason why this issue was intermittent is because each and every time they were sending this test probes, they were able to hit the congestion problem, and the test probes were not always sent. It is sent in an intermittent fashion. So that is the reason they were able to see this intermittent pattern of issue. But the routing table issues were always there because of this misconfiguration. Okay, so now it's time to validate for the fix. So let's start this test probes in the background while we ping from the server 1 and server 2, and let's observe the things. Okay, the test probes are started and the ping is going on, and we can see that from the server 1, in order to like, so server 1, while trying to ping the server 2's IP, the 192.168.252, and now even though the test probes were running in the background, we were not able to see the congestion problem. The reason is now we resolved the incorrect path forwarding of the test probes, which was causing the congestion earlier, and because of that, the larger congestion problem is also resolved, and now the latency problem is gone. Okay, since we figured out the problem, now it's time for us to summarize the troubleshooting steps which we used in this scenario. Initially, we were presented with a scenario where the issue seems to be intermittent issues, where the customer was able to see the latency on high latency on the network intermittently. And one such flow which was impacted is the server 1 flow towards server 2 during the time of the issue. And we were focusing on ping flow between the server 1 and server 2 because that was also impacted. Okay, and then later we identified spine devices were the ones which were adding this latency on the packets while forwarding it towards LE3 and LE4. And we figured it out with the help of DMF packet recorder node packet captures. And then we figured out that the spine was adding this latency because of the congestion happening on the interfaces facing towards leaf 3 and leaf 4. So later we were able to focus on more things based on that. But this information was figured out with the help of CVP's event dashboard. And then we figured out the cause of the congestion. The cause of the congestion was related to some incorrect path forwarding happening for some high bandwidth test probes sent from the servers connected to leaf 5. And these probes were unfortunately forwarded towards spine 1 and spine 2 due to incorrect routes pointing towards spine 1 and spine 2, and that was causing this congestion. So we figured this incorrect path flow with the help of CVP traffic flow dashboard. And then finally, we logged into the switches directly to figure out there was a misconfiguration on leaf 3 and leaf 4, which was advertising an incorrect /24 route, which was actually drawing all these high bandwidth test probes towards the leaf 3 and leaf 4, causing the congestion on spine interfaces facing the leaf 3 and leaf 4. Okay, once we fixed this misconfiguration on leaf 3 and leaf 4, we were able to fix the larger congestion problem as well. Okay, so that's a wrap for the troubleshooting scenario we had for today. Please feel free to post any question related to the scenarios we were using in this session, and also any tools which we have used. So we are very much happy to answer that. Thank you. And with this, I will hand over to Lokesh again.
Thank you,
Lokesh, over to you.
Vignesh. Thank you so much. And like, this was really in-depth, step-by-step troubleshooting, and just blew my mind personally. Like, I mean, how DMF and Cloud Vision were able to come together to sort of like, troubleshoot this congestion issue what we had in the network. I really hope that This session was useful for all our customers, and this is really great technical stuff what we presented today. Again, to all our customers, recording for these sessions, today's session will be available on our Arista community page, along with the presentation reference material and the questions what we covered as part of the webinar. But I would also like to highlight that along with these materials, what we are putting as part of the tech webinar series, there are a number of other good articles which are available on the Arista community that can be helpful for various other topics. So I definitely recommend everyone to leverage that knowledge base. Our next session in 2024 series is scheduled on 28th of Feb at 11 a.m. Eastern. Really looking forward to see everyone on that session as well. And taking a cue from today's technical deep dive, what we just went through, if you are interested in scoping a custom training session with us or just interested in learning more about the TAC custom training, please do reach out to us on tac-custom-training@arista.com. We are also putting a feedback form with the 3 to 4 questions in the chat window. So I definitely recommend everyone to provide your valuable feedback, because we definitely intend to use it for our future sessions. And with that, I'm going to keep the webinar open now to wrap up on the Q&As and to answer any questions that you may have. You can utilize our Q&A manager to ask our questions, ask any questions with our technical leads at this point. What is the email for the TAC again? Vignesh, could you please go to the last slide? I think it'll be helpful to, yeah.
Yeah, sure.
Just the last slide. Yeah, perfect.
Yeah.
Thank you. That's the email for the custom TAC training is tac-custom-training@arista.com. I think there was just a feedback that you were not able to access the feedback form. Apologies for that. I think you should be able to access it now. Thank you for the great feedback on the presentation. Really appreciate it, guys. Okay, I think we are done with all the questions at this point. So if there are no other questions, then we'll wrap it up. Thank you, everyone, for joining us today. Looking forward to seeing you on the next session. Thank you. Have a great Wednesday.